predict the variabilities. But this one is like yeah, we just have a bunch of people and think, yeah, we should like start to do the solar geoengineering. And also we found that like as we know, the El Nino Southern Oscillation is one of the largest climate system that influencing like global temperature distribution, hydrologic cycle, or even like ecosystem. But we found that there are not a lot of study about like how does its response to solar radiation management. So yeah, and this study we basically gonna focus on two major solar geoengineering strategies. The first one is most well-known one is like a stratosphere aerosol injection, and the second one the marine cloud brightening. Yeah, and the here first about the stratosphere aerosol injection SAI, it's basically can be known as it's like similar to the effects of tropical large volcanic eruption that it will spray the sulfate aerosol or sulfur to the lower stratosphere, and it will reflect the incoming solar radiation, decrease shock radiation to Earth, and make the cooling effects on Earth. And here the SAI experiments we were using is like use the ARAS project outputs, and it has 10 ensemble members, which is pretty good. That since we were looking at the ENSO variabilities, it's one of known for like its large internal variabilities, and large ensemble members can like isolate the force signal. And the forcing time series like it's the experiments like span from 2035 till the end of like 2069, and it's forcing is changing over time because of the greenhouse gas concentration is also increasing. And also the marine cloud brightening experiment. It's not the same as SAI spray the aerosol in the stratosphere, but they mostly focus on the boundary layer. It brightening the stratus boundary like boundary layer stratus, and it will reflect more like solar radiation. So it's also like making a cooling effects. And the MCB experiment here we use is run by Jack's team. I believe it's also part of the ARAS project. And here we're going to look at only the 5% CD mask experiment that it also has like 10 ensemble members. And the CD mass area is based on the most susceptible stratus, the cloud regions. And as you can see, like it mostly around the Northeast Pacific and Southeast Pacific and some part of Atlantic and Indian Ocean. And it has a similar global warming scenario, SSP245, but use not the high top CSM model, but the CAM6. And yeah, and here are their like their global mean surface temperature performance. We can see that both of the MCB and SAI cools the global temperature for like a 1 degree, even though the SAI kept the global mean surface temperature at a really stable level, but MCB is like making it like a decrease in the first 5 years, but after that it's have a slightly like increased warming trend because of their forcing they use. It's a constant for each year. And maybe just quickly jump into the ENSO that we were focusing today. And the first thing we were really curious is just like, yeah, let's just look at their the most like well used index, the Niño 3.4 index, which is the like average surface temperature over the Niño 3.4 regions, to say it's a really good like index to represent the ENSO variabilities. And here are the 4 experiments. The first 2 on top are the geoengineering reference run, which are the global warming scenarios. And the bottom ones are the SAI and MCB. And among all of them, there's a really noticeable change, which is in MCB, as you can see that there's a really strong decrease in the first after the injection or as environment starts, and then it has a very low variance that feel like so it's trapped in like a weird behave that it can't really have as strong as the others that it has large wiggle lines. So we kind of want to like have a deep understanding of it. We look at the variance of ENSO index. Here's the 10-year moving standard deviation of the Niño 3.4 index. And as we already seen from the time series of the Niño index, that there's a strong variance change in MCB. And this is pretty shocking that the variance change is like a third of the other experiment. Yeah, all the 3 other lines are the global warming scenarios and the SAI experiments. And the MCB basically is like giving decrease the variance a lot, and kept it in a stable state after 20, after like maybe 5 years. And we look at the magnitude change of separating both the El Nino and La Nina events by grabbing all of the events out and doing like a composite all of them together. And here the 0 months means the peak phase of El Nino or La Nina. Usually we know that the El Nino is like having a developing, like increasing, getting warm trend in the developing year, and peak in the winter time, having like over here it's like over 2 degrees Celsius warming. And in the decaying years, the El Nino is like getting weaker and developing, like cooling, evolving to a La Nina or neutral phase. But in MCB, it just starts with a little warming here, and it won't give a strong warming trend, and the peak phase is like also maybe a third of the normal warming, and it's slightly decaying the following years and become like a neutral phase. Similar things also happens to La Nina, that MCB like strongly, there is a really weak La Nina in MCB experiments. And other than the magnitude, we also look at the frequency change. This is a power spectrum of the Niño index. Usually we know that there's a really strong period, the 2 to 7 years for ENSO, as we can see from here. But it seems like in MCB, this frequency like peak is also missing. So we kind of get a sense that ENSO is experiencing a really weird like in MCB, which is not like just slightly change, but it's a really dramatic change, I can say. Firstly, we want to understand the mechanisms, like we want to go through the mean state change, as we know that mean state could like modulate ENSO variabilities. So here it's first it's like some the surface temperature change and precipitation change compared to the global warming scenarios, right? And the grains are the mask are the like the green lines are the masking the forcing region for MCB. As we can see, the forcing regions like giving the MCB giving the like cooling effects, but they also triggered a really strong like response specifically over the Pacific Ocean. That it forms like negative phase of the Pacific decadal variability with strong cooling over the tropical Pacific and two warming centers over the exotropics. And they're also like cooling anomalies, noticeable anomalies over the North Pole. And also the precipitation patterns is forms like it indicates the atmosphere change. And the ITCs is like strongly damped a lot, like because of the weekend of the decrease of precipitation, and seems like it's moving northward. And also there's a precipitation a positive anomaly that is like over the tropical Indian Ocean, the maritime continent. So there seems like a lot of strong response in MCB, but in SAI, even though they give a similar cooling for global mean surface temperature, but it has the SAI is like giving a more even distributed global surface temperature. Even though there's a slightly like we can also tell the over Pacific, they're like a little stronger cold tone anomaly, but compared to MCB, this is a really weak change. It's like really unnoticeable. So to understand what is going on in MCB, since we also noticed there are definitely some atmosphere response changing that influencing the aerosol interaction or ENSO. So here we're going to introduce the moist static energy analysis. It's really helpful to understand the thermostatic stability by separating the dry stack energy part and the latent static energy. The latent static energy basically represents the specific humidity change. And here is a cross section of the static energy over the tropical Pacific, and I marked the this is the Pacific regions, and as we can see, there's a strong decrease like over the lower troposphere in static energy, and it's mostly contributed from the latent static energy change, which means there are a really strong drop. And the dry stack energy.
You have 5 more minutes.
Oh, thank you. Dry stack energy is mostly like on the upper troposphere. And this dry stack, the decrease of energy, especially from the MCB, like make it super dry, is causing a strong subsidence rather than like if there are not enough energy to make convections. So their strong subsidence dominates the Pacific Ocean, and it will shape the subsidence. Since we know there's a worker circulation over the Pacific, the subsidence branch is strongly strengthened, and work circulation, they'll push the convection, like move even westward and to west, like maritime continent. And the subsidence is also like causing a divergence at surface, and also along with the temperature gradient or zonal gradient around Pacific. So the we're thinking like maybe the trade wind is also changing in MCB. And here we found that the trade wind is the magnitude is strengthened, and also it's to its seasonal cycles. And it is found that many studies found that trade wind strength could really like decrease the magnitude of El Nino, since it will bring a lot of cold water from Eastern Pacific. Well, for SAI, they're still like not really strong change compared to MCB. And for ocean response, here's thermocline feedback is one of the crucial things that communicate the the ocean with ocean surface, that bring a lot of like cold water to ocean surface. And usually we know there's like a lot of warm water in the warm pool, and it forms the like tilted thermocline to the Eastern Pacific is like thinner. But in MCB, the warm pool water is like getting way more because of the weakened air-sea interaction, because of the subsidence or like cooling effects, and it forms like a stronger tilted thermocline and bring a lot of cold water communicate to the atmosphere, and like could dampen air a lot. And so we want to like quantitatively analyze the previous those feedbacks, like the trade winds one and also the thermocline feedbacks. Here we also know those are like weakness feedbacks. So we want to use the mixed layer heat budget to quantitatively analyzing them. I'll just show the result here, time limits, and we found that MCB, all the feedbacks basically gone together. They're not a specific ones like damping or, but it just everything's like all the air-sea interactions are strongly dampened, so it will contribute to this weakened warming tendency to the Eastern Pacific. So we kind of hypothesize that this mean state change is strongly modulating air ENSO variabilities in MCB because of the cooling from the MCB forcings. Then it triggers stronger trade wind, and it will stop some of the west wind bursts or intraseasonal oscillation to generate El Ninos. And also in the same time, because of the weakened air-sea interaction, that forcing the ocean to have a really strong tilted thermocline, and also like contribute to the cooling effects, like dampen the ENSO a lot. So here's a brief summary. So we found like basically found because of all those mean state change that ENSO is like dampened for like a third, 2/3 in MCB, but they're not strong influence like comparable change in SAI. And we found that we discussed some mechanism, but we think this is going to be a really interesting topic to start with, since this is really an extreme circumstance that they're not of. We can't imagine there is no ENSO in like our system or some or like in a simulation. It could be an interesting thing to imagine, like a world without ENSO. It may be a good thing or not good thing, like other because of its teleconnection or ecosystem influence. So yeah, I will stop here. Thank you guys for listening.
Thank you very much. Very, very interesting, nice talk. And okay, I open it up for questions. Please raise your hand or type questions in the chat. You can stop sharing if you like. Does anybody have a question they want to ask?
Yeah, I've got a question. I don't think you can raise hands when it's not a meeting. It's Andrew Lockley. There were two things I want to ask. So firstly, is this dependent on the MCB regime? Could you conceive of MCB regimes that don't have this effect? And also, did you look at the possibility that this strong increase in subsidence might prevent the aerosols getting into the boundary layer and therefore stop MCB working at all? Or did you assume that MCB was going to work when you did these experiments?
That's good questions. First question I want you to be clear a little bit. It's like, are you asking about the region of MCB force inside proposal matters?
Well, yeah, you could do MCB in different places at different times to different magnitudes. And if you felt that preserving ENSO was important, is it conceivable that a regime could be developed that would allow us to preserve ENSO?
Yes, that's totally. I think there are some studies found that the Southeast Pacific might be other like specific, like really important regions that could trigger the atmosphere response in the ocean that causing the La Nina like and yeah, and here in this experiment is we only looking at the like most susceptible regions, so it just gave us a really maximum like last aerosol inject or like most profit. So but we also definitely like could use it on other regions to like avoid this thing happen, but putting more like aerosol in other places. And about your sorry, what's your second question?
Yeah, would this strong subsidence just prevent aerosols reaching the boundary layer and stop it working at all?
Yeah, the subsidence definitely could cause like we were also think about this like feedbacks that what's gonna happen to the like atmosphere response that causing the aerosol distribution like change. But I'm not running this model. It's from John Jack, but Jack Chen, but he they're using the like a prescribed the cloud droplet concentration, so it will just force it at a certain level. It won't have a strong fluctuation as I look at the short radiation over that region. So it's like it basically have no strong response, like feedbacks from the atmospheric conditions. Seems like, correct me if I'm wrong. I'm not.
Yeah, they do prescribe the cloud droplets. Yeah. Next question. Hongwei, you wanna ask your question?
Yeah, thank you. Thank you, Chen, for the great talk. First I have comments about your last question. Actually, it's just I'm just wondering whether you or maybe because based on the MCB apply map you show from Jack Chen, it seems like you have like several areas like Southern East Pacific, Northern East Pacific. I'm just curious whether this ENSO shutdown is caused directly by one area or like by the combination of all the area. This might maybe worth checking. Maybe for some area when you do MCB, whether it's always caused ENSO shutdown. My question is, go ahead.
Sorry, please go. Oh, yeah.
Okay.
Oh,
yeah. I was going to ask, my question is, so when you show the surface temperature change due to MCB, it feels like there is a very large decrease of temperature in the North Polar area. I'm just curious whether have you checked what caused that?
yeah. First of all, the North Pole part, I didn't check. I only look at the tropical, all the mechanisms, even with the ocean, and I haven't even checked the like there are some mechanism like from the actual tropics influence could also happens, but it seems like the major concern is still like the force itself since the MCB forces over the like K regions of ENSO dynamics, and also it's to the another question, the MCB forcing regions, that also like we were thinking to maybe do experiments of like about that since, but I remember there a study from University of Victoria. They already found like did the separate different regions to do the MCB forcing, and I remember their maps give that the Southeast Pacific gave the most strong like La Nina cooling response, if I remember correct. Yeah.
Cool. Thank you.
Yeah, thanks.
Okay.
Any other comments or questions for Jen? You can type it in the chat. And maybe while you're thinking about it, David, you can start getting ready. Share your screen.
Okay.
So I guess that's it, Chen. Thank you very much again. That was a great talk. And we move over now to David. Can you please also introduce yourself? And I let you know after 20 minutes, after 15 minutes that you have 5 minutes left.
Oh, good. Thanks.
Thank you.
So yes, I'm David Mitchell. I've been working at the Desert Research Institute all my career and studying mostly cirrus clouds. And this is a culmination of a lot of work over the last maybe 15 years or so. One of the main uncertainties about cirrus clouds is how the ice is formed or produced. And there's two basic mechanisms, heterogeneous and homogeneous ice nucleation. And we're trying to kind of parse out in nature which mechanism is dominant. And we've made a lot of progress through satellite remote sensing, I would argue. And some of the findings led to some clarity just looking at the skies. So these are some wave clouds over, and cirrus clouds in general, over the Sierra Nevada behind Reno. And the optically thicker clouds, we would argue, are the dominated by homogeneous ice nucleation or home cirrus. And the more diffuse optically thinner clouds are the het cirrus. So I'll try to show the reasoning behind all that now. And also the logjams, that's one logjam is the mechanism for ice. The other logjam is more technical, and it involves how the pre-existing ice is treated in cirrus clouds and climate models. So this is our satellite retrieval, the equations that go into it. The improvements that we made over the past method is we're now using the ratio, we're retrieving the number concentration divided by the projected area of the size distribution. And this is all related to the absorption optical depth ratio, which is called BEF, beta effective here. We also retrieve some other, anyway, that's the main improvement for N. And then we improve the ice water content by using the Irfani-Mitchell treatment. And we also improve the effective diameter. The theoretical definition is, at least one of them is given in this paper here, but you can expand that. So you get these two ratios where the ends cancel, and you are still using that same equation, but now you're able to retrieve it because N over A is a function of the absorption optical depth ratio. There's this relationship that I'm not showing, and also the ice water content over N. So you can retrieve both of those. You can also get the ice water content and the extinction coefficient. So the key points are that we're sampling single layer cirrus clouds, and they're semi-transparent so that the calliope LiDAR can penetrate them. And then number two, most of the clouds have visible optical depth less than 3. And third point is that the imaging infrared radiometer, IIR, is sampling cloud layers. We're not looking at profiles within the cloud. And the fourth point is the sampled clouds have a radiative temperature less than or equal to 235 Kelvin or minus 38 C. And these, number 5, the ratios of N over A and N over I sweater content and the absorption efficiency 1 over that. They're all functions of this absorption optical depth ratio that were derived during field campaigns. And you can calculate that from the size distribution data and radiation theory. So we're also, number 6, using 4 years of Calypso data here. So we can compare these retrievals with the results of Martina Kramer's climatology of cirrus clouds, published in 2020 ACP. And we're looking at the orange and red curves are thick cirrus clouds, so you can ignore that. Just look at the blue curves, and that's for all the optical depths that we're sampling, which have a range of 0.005 to 3. And for number concentration in the lower left quadrant, we're within about 25% of percentile uncertainty of the Kramer results. So we felt that was adequate. And ice water content in the lower right is also agreeing pretty well with the blue curves with the Kramer ice water content. And up in the upper left is basically it's the ratio of ice water content over number concentration. So there's no new information there, but that's also compared with the Kramer data. So these we found that the homogeneous, what we think is homogeneous ice nucleation in these cirrus clouds is mostly affected by the number concentration, or the number concentration and the ice water content are mostly affected by homogeneous nucleation, or we can call it home. So when home is observed over land, the effective diameter also decreases. So both ice water content and effective diameter are affected by home. And the extinction coefficient is shown here. That's the formula. So it's a good metric for separating out these two mechanisms of heterogeneous and homogeneous ice nucleation. So when we do that, we get these plots here where we're using all the samples over oceans. And these triangles are predicted by a very simple microphysical model. It's basically homogeneous ice nucleation theory that I'll show in a moment. But the ice water content is in the body of the plots, but it's temperature, radiative temperature on the y-axis, log extinction on the x-axis, and the colors inside the triangles for ice water content on the left side are matching the retrievals. So that was encouraging that theory is agreeing with the satellite retrievals. And on the right side, we have number concentration where this is over, I should also mention that we're looking at the mid-latitudes and the high latitudes here. And WIN means winter and SUM is summer. So you can see with number concentration how the two mechanisms are separated. So the heterogeneous ice nucleation always will give you relatively low concentrations of ice crystals, and the opposite is true of homogeneous. So you see a gradient in number concentration from left to right, and that's due to the increasing activity of homogeneous ice nucleation. The theory that we have for the triangles is pure homogeneous ice nucleation. So that should line up in terms of the colors with the right side of the data here. And it does. And then this is the theory that we use, simply the Clausius-Clapeyron equation used to predict the ice water content, and also the supersaturation that's predicted for homogeneous ice nucleation here. And those two formulas together give you the vapor density at corresponding to homogeneous nucleation conditions, and also the vapor density for ice saturation. And the difference gives you the ice water content for homogeneous nucleation. And then you can do some more things to get the other quantities, such as using the mean diameter during field campaigns for the calculation of the effective diameter. There's some formulas you can apply to convert d mean to effective size, and similarly for number concentration. So here are some more results where we look at the effective diameter, comparing that with the satellite. So it's predicted here for pure homogeneous nucleation. And the main interesting thing perhaps is the looking at the counts or the sampling frequency on the right-hand side here for ocean, for the summer and winter and the mid-latitudes and the high latitudes. The dark triangles, black triangles, show that the frequency of homogeneous nucleation is low, or the probability is very low, because almost all the samples are in the middle. So that's what we expect, basically, that homogeneous nucleation doesn't occur very often in nature. So this is how we tried to parse out the two mechanisms, the heterogeneous, homogeneous. We found that there's a maximum in when you plot effective diameter versus extinction. Again, extinction is a good way to separate the mechanisms. You can see this vertical dashed line is separating the two mechanisms for the warmest temperatures, as just an example. And on the left side, it's heterogeneous, right side is homogeneous nucleation. The particle sizes drop on the right side due to the vapor competition effects, we believe. So homogeneous nucleation produces a zillion crystals, a very high number concentration compared to Het typically. So that competition for water vapor makes the crystals smaller, and that's why it's going down, decreasing on the right side. So using that separation mechanism, we also go to these colder temperatures, and we lose the maximum at the coldest temperatures. So we're on the lower panels here, this corresponding to the same regions and seasons. The horizontal dashed line is where we lose any signature for homogeneous nucleation. In other words, there's no more maximum in the effective diameter curves at the dashed line. So those two things bound a region that we argue is characterized by strong homogeneous ice nucleation. It's relatively impactful on the size distribution. So it's a rather conservative estimate, in other words. And so using that method, where we define a certain region in the home space, you might say, we get the fraction of homogeneous ice nucleation for these different seasons: December, January, February, and June, July, August. And we also, so the darker the green, the greater the fraction of homogeneous. And we also found that when there's more dust, the home fraction is lower, like over the Southern Ocean, compared to the wintertime. And so there's less dust in the wintertime. And the same in the Northern Hemisphere, you have the Asian deserts. In the summertime, there's a lot of dust coming out of the Asian deserts, and that propagates across the Pacific, and it seems to be decreasing the home fraction. So in the wintertime, the home fraction downwind of the Asian deserts is much higher. So there might be some natural cirrus cloud thinning going on in nature. So that is what we use to say that is a paper by Freud et al. In Nature Geoscience 2022. And in the Asian, this middle panel here, upper middle panel, shows most of in the northern hemisphere, most of the dust is coming from Asia during the summertime. And another paper by Koch et al. Shows that in the lower panels here, most of the dust in the summertime is coming over the southern hemisphere, is coming in the summertime as well. So that's where we got that. And
5 more minutes now.
5 more? Okay. So these are the main thing here is the thick line, the thick black histogram separating the home fraction from heterogeneous nucleation. So the upper panels are for homogeneous, the fraction of homogeneous nucleation. Lower panels are the weighted fraction, weighted by optical depth. So that is more important from a radiation standpoint. So it's a proxy for the cloud radiative effect in the lower panels. And it's over 50% in the wintertime outside the tropics. So it argues that the home cirrus clouds are radiatively important. And I'm running out of time here. So we used the radiation transfer model to look at this over the Arctic during Arctic night at 70 degrees north latitude. A dissort model, LibRadTran is the model we used. And we have profiles for ice water content versus height, effective diameter versus height. The main change was that ice water content, this is from the retrievals that we have over the Arctic and in the wintertime. And we divided it into 4 different cloud types, about 1.3 kilometers each, but having different cloud base values. And the result of that gave us these differences on the cloud radiative effect for top of atmosphere and at the surface, which is only long wave radiation happening because it's Arctic night. And it's around 10 watts per square meter at the surface and in the atmosphere on the right side. So the atmosphere changes affect the geopotential heights. And if you apply the home fraction of 0.3, which we retrieved, the overall effect is about -3 watts per square meter at the surface. And then that's assuming overcast conditions. So it's something less than that, for typical cirrus conditions. But it does show that there is some cooling. And then really quick here, this is the thing that we disagree with, and the way that pre-existing ice is treated in climate models. Basically, I don't have time to go into the details, but most of the ice is produced at cloud top, as shown by De Coitzides here. Homogeneous nucleation is the dominant mechanism near cloud top. That's also supported by this modeling study by Spitztinger and Gierens. And this term for pre-existing ice is a layer average. It's not at cloud top, it's just the average for the layers, which is about 700 meters thick in the ECHM6 model. So you need to really have the ice mixing ratio for cloud top, which might be about 1/10 of the 1/5 or 1/10 the value of the average. So that's the main issue here. And this is the reasons for questioning the pre-existing ice treatment that I just explained. And the results that we're getting from the satellite retrieval with the home fraction estimates, that probably wouldn't happen if you had pre-existing ice the way the models are treating it. So I strongly doubt that the models are going to give you the home fractions that we're retrieving. And we're being conservative about it as well. So we strongly suspect there's a problem with the pre-existing ice treatment in the climate models. Thank you. That's the end of the talk. And thanks for listening.
Yeah, that was great. If there are any questions, go ahead. I can start with the question on the pre-existing ice. It's very interesting. Do you want to stop sharing? Then we can see.
Yeah.
Just looking if there are questions. But yeah, so the pre-existing ice is in chem, it's probably in other models, and you're saying that it really doesn't reproduce the homogeneous freezing in that point. So what does that mean for climate effects just without cloud seeding? Does that mean that the long wave radiation isn't represented properly?
Right. So we compared the Wacom for cirrus clouds, the Wacom effective diameter and number concentrations, and they're really, really different than what we retrieved with this retrieval. The number concentrations were much lower, and the effective diameters were maybe a factor of 3 larger. So yeah, it would make a big difference in your radiative transfer in the models.
Yeah, certainly something to look into. Yeah, thanks. There's a question by Hongwei in the chat asking if you could explain, since you correlated extinction to use it to separate heterogeneous and homogeneous nucleation, how that works.
Yeah, the homogeneous nucleation is affecting mostly the ice water content and the effective diameter. And the extinction coefficient is basically the ratio of those two. So any home activity in the cirrus clouds is going to affect the extinction coefficient the most of all the quantities that we know of, that we can retrieve anyway.
Yeah, does that
you.
make sense? Yeah, okay. And there's Glass also. Please unmute yourself. Hi.
Hi. Thanks, David. That was a nice talk, and I like particularly that you use this offline radiative transfer model to get the numbers. I think that's new, right?
Right. Yeah. Thanks.
So, yeah, actually, what if you it will be interesting to now also go back to the climate models and see which of the climate models, or what do climate models produce in terms of radiative forcing, because the numbers that you got, I think seem really reasonable. But on the other hand, if you think about a forcing of 3 watts over a region as small as the Arctic, yeah, I'm not really sure how much, how big of an impact that on the climate would have. I mean, certainly would have something, but I could imagine actually some of the modeling studies from through the Storelmo, where the impact was quite big, might have even a larger forcing. And I also just wanted to comment on the pre-existing ice. I think that's certainly an issue, and there are some people saying we should use it, some people not, but I would say that going further and going on to high resolution models, or using LES type of cloud resolving models, well, anyway, when we go to these resolutions, we will stop using that pre-existing ice. That will naturally not make any sense to use that. So I would here advocate rather for some more studies using this type of models, and that may give us some new insights on that.
Yeah. Also, we are incorporating these satellite retrievals into the CAM6 model right now. Ehsan Irfani is doing a lot of that work, and we should have results at the AMS meeting. So stay tuned on that. Like your comment about how much would this affect the whole planet is a good one. You know, we have the same question. So that's what we're trying to find out. We're actually using the satellite retrievals to constrain effective diameter in the model. And through the effective diameter, that should change the ice water content because of the false speeds. So we'll see what happens anyway.
Yeah, thank you. And also maybe I can comment just quickly on this pre-existing ice. So I think the original idea of using this pre-existing ice was because the models produced too many ice crystals. So and now it seems like the outcome of that is, at least in this Wacom version and maybe some other models, that is just the opposite problem. But I think that was the initial logic for putting that description beyond some physical reasoning. But yeah,
it's also important where you do your field campaigns. Like the thick clouds are going to have more home activity than the thinner clouds. So if the pilot in the aircraft is targeting the pretty thin cirrus clouds that are probably heterogeneously dominated, then you're going to skew your, average value, which is considered as ground truth all the time in the community. So it's important for flight notes, maybe, the pilot should make notes about what kind of cloud they're sampling and give the users like us, more understanding of things.
Yeah, that's a great point. Thanks. Any more questions for David? I think we had a great discussion, really nice talks. You can still raise your hand if you want, but I want to thank you all again, David and Chen, for presenting. I want to apologize again for our confusion with the web link. I hope that we have everybody here and not somebody still waiting on the other side. And I also want to remind you, if you haven't yet, to apply to attend the Gordon Research Conference, which is going to happen next year in February in Italy. There's also the Gordon Research Seminar. And so, if you need the website, you can just Google it, Gordon Research Conference for Climate Engineering 2024. And hope you all can make it to that as well. Okay, with that, I wish you all a nice Friday or rest of the Friday and a good weekend, and then see you next time.